Okay, so then I would like to continue and talk about histograms of intensity values of images. So we can actually use a histogram to represent the distribution of intensity values of an image, and the modification of this histogram allows us to make certain image processing operations like changing the brightness or changing the contrast of an image. And the second thing we're going to do today is point operators. These are transformations of images which transform the image into a new image, which have some advantages. For example, that they change the properties of the histograms that we are considering. So if I look to a typical image, this is kind of a small 3x3 image. As I said, we have a grayscale image, and this can be seen as a matrix with different intensity values, typically between 0 and 255, which can be mapped to some grayscale images. So this matrix would represent an image like that. And what I now can then do is I can actually build a histogram from this image. And the histogram stores the intensity values and the number of times this intensity value actually occurs. So if I would say, how often does the value 0 occur in this image? Actually, 1, 2, 3, 4, 5. So the histogram for intensity value 0 would be 5. Then for 1, 2, 3, 4, 5 until 127 would be 0. For the value 128, I would get 2 entries. Then zeros again until 255, we'll get a 2 again. So it would be 5, a couple of zeros, 2, a couple of zeros, and 2. That would be the histogram of this image. Of course, in this case, the histogram is larger than the image itself, but this just is the effect because the number of pixels in this example is so small. If I have larger images, the histogram is typically smaller. Of course, the histogram only stores the number of elements that the histogram needs to store is just the number of possible gray values. Okay, so the histogram h of g, of my grayscale image g, is defined as the number of pixels that take the value g. And I vary g from 0 to the maximum possible intensity value that I have, typically 255. So I have 256 pixels, values, counts, which tell me, whatever, h0 is the number of times I have an intensity value of 0. h1 is the number of times I have an intensity value of 1, and so on. And this is the histogram. So what it does, it counts the number of pixels that in that image that take a certain value g. And then I can also, if I divide this histogram by the overall number of pixels that I have, I actually obtain a probability distribution. And this is, so P of G defined as the histogram divided by the number of pixels give me the probability that a random pixel somewhere in my image takes this value G. So in my example before, we had so I had this histogram where 0 took the value 5, then a couple of zeros until 128. This had a value of 2. And in the end, also had a value of 2. I have 9 different values. So P of 0 would be 5 over 9, or divided by 9. P of 128 would be 2 divided by 9. It's the same for 255, and the rest would have a value of 0. This is exactly this probability. So for every single, or I can compute for a random pixel the probability that this value takes intensity value G. Okay, let's have a look how this looks like. So I have a couple of images. Hope you can see the difference. It's pretty bad in the projector, but you should be able at least to see that this image is kind of darker than the other image. And down here you see the corresponding histograms. So this is from 0 to 255 and the number of times this value occurs. So what you can see here is there's, for example, a large number of bright values, potentially these guys over here, maybe some in here. And what you see in here is there are actually no values which take the color black. So they are start somewhere in the middle, let's say 128 or something like this, maybe toward the end. Here it's exactly the other way around. Here the whole histogram sits in this area, so it's pretty dark. And here it's somewhere in the middle, so it's kind of compressed in the x direction. And I can see different images corresponding to the different histograms. So if I change, what I can do is now I can do an operation and change, or make a mapping that changes this histogram. This then also changes the image by just, of course, changing the corresponding values. So for example, if this would be my input image, I would say, okay, there are no really black areas, there are no real white area, so may I just increase the contrast of that image. That correspond to taking this histogram and stretching it in this direction. If I would do that, stretch that to the outside, I would end up with something which is very similar to this image over here, where I then have all the values occurring properly, or in a way that we as humans at least can interpret those images better. So the histogram of an image tells me something about the image. And I can, as we will see later on, define transformations which actually exploit those histograms in order to improve the quality of the images. In terms of improve the quality of the images so that we as humans can better interpret those images. Okay, so the first question is, how do we compute the histogram, such a histogram? What is the algorithm to do that? So if you get the task of computing an histogram given an image, how would you do that? Ja.
Man könnte beispielsweise das Bild iterieren und beim oder ja, wenn ich einen Wert erhalte, dann komme dann einfach den zugehörigen Wert einzeln.
That's exactly the way it works. So we allocate a vector for storing the histogram. So in this case, 256 different values. We initialize it with 0 counts, and then I iterate over the image. So I just inspect every single pixel, said, okay, this pixel number 1 has a gray value of whatever, 50. So, okay, I go to the 50th position of this vector and increase it by 1. Here's the second pixel. It has a value of 100. So I go to the histogram to the 100 bins and increase the value by 1. And I do that for the whole image. What is the computational complexity for doing this operation? So have you heard about computational complexity, O notation? Yes? No? Good, good. Yes. What is the computational complexity of such an operation? How many operations do I need to carry out in order to do that step, in order to compute the histogram, depending on the number of pixels that I have? Ja.
Das müsste zweimal n sein. Einmal der Zugriff des Pixels und dann Schreiben ins Histogramm.
Okay, it's definitely a linear complexity. So I don't really care about this constant factor if it's 2, 3, 4, 5. This basically depends on how this is implemented in hardware. But it's a constant number times the number of pixels. So it's a linear dependency between the size of the image and the computational cost to compute the histogram. So if I have an image which has twice as many pixels, this operation will take double of the time. If I have an image which has 4 times the number of pixels, this operation will take 4 times as long. This is what is called the linear complexity, computational complexity, O of n. So it depends on the number of pixels that I need to consider. It also depends on the number of grayscale values, but typically the number of grayscale values is constant, therefore it doesn't occur here, because I need to allocate a vector of the size of the grayscale value. So if I have an image or a representation where I have millions, trillions, or whatever, a variable number of intensity values, I would get also a factor in here an additional factor, so it will be n plus the number of grayscale values. But this is something which is irrelevant in practice. In practice, the only thing which matters here is the number of pixels that we have to consider. Okay, and the algorithm, as I said, works very straightforward. I take a vector h with length 256. If I would use a 16-bit image, this would be 65,000 plus something. I initialize it with 0, so I have to visit every element of this vector once and set its initial value to 0, if my compiler doesn't do that for me automatically. And then I go through every pixel of the image, and I increase the element in this vector, the index, the gray value. I pick up the gray value at pixel ij from the image and increase the corresponding value of the histogram by 1. This is plus plus. This means just adding plus 1. That's it. As soon as this loop is finished, I'm done. I've computed my histogram. Okay, so how does such a histogram may look like? So this is the histogram of an image that I have, and these are my values from 0 to 255, and this may be a histogram. What I see is here a larger, let's say, dark gray area, and a larger brighter area, and some intermediate values. That's what this histogram tells me about my image. What I also can do is I can look to the cumulative histogram. This means for every element in here, I compute the number of pixels that have the same or a smaller gray value. So what I can do is I can take the value 0 is exactly the same value 0 of the histogram here. So this 0 and this 0 are identical. The value 1 in here consists of taking the value 1 from here and adding it to the value I got from 0, so one element before. And then 3 is a value of 2 plus 3, 4 plus 5, and so on. And then I get a cumulative histogram. So I end up here with n with the number of pixels. So for every point in this histogram, if I take this value over here and read this value, so this is, let's say, n times 2/3, then I know that there are n times 2/3 number of pixels which have a smaller intensity value than this one over here. So it's kind of the sum over the individual values over here. So every element here is given by the corresponding value here, the sum of all those values. Was there a question? Okay. Is there any question? Is this clear? You know what a histogram is? You know what the cumulative histogram is? Okay, good. We can then turn that, as we said, into into a probability density function of values and also the cumulative distribution function by just dividing the histogram and the cumulative histogram by the number of elements, the number of pixels that I have. So as a result, the sum over all those values will be 1, exactly given by, this is wrong, this should be, I don't know, this is h, so it's fine, just the same image before. But if this would be f of g, this value would be 1. So it's maybe I took a suboptimal image here for illustration, I have to admit. So this is, what is shown here is this hg and not fg. Just kind of these values divided by n, so I end up with a value of 1 over here. Okay, so far, so good, everyone on board? Okay, so now let's analyze those histograms, because the histogram tells me something about the image, as I said before. And if I have such a distribution now, what are standard ways for describing distribution? Some key values. The moments of the histogram, the key moments. So mean and variance are, for example, two ones which I'm typically interested in. So I can now take these histograms and simply compute the mean value of this histogram. And I also can compute the variance, or I can compute the median of this histogram. So these are three important characteristics of a histogram. For example, the mean describes the average brightness of the image. So the higher the mean value, the brighter the image is. So if I go back to this example over here, so the mean value will be sitting maybe somewhere over here. It's lower than the mean value of this image, which will be something sitting over here. So you can see already this is brighter than this one. So the mean value tells me something about the brightness of the image. And the variance, this tells me something about the contrast of the image. So if all values are concentrated around a very, very small area, it's an image with a very low contrast. If they spread around the overall image, it's typically an image with a higher contrast. And the median is just kind of a robust description of the brightness. So if you have a few outliers, they are not, they don't affect the computation of the brightness as much as the mean would do. Okay, how to compute the mean? How do I compute the mean of such an histogram or of my image? My intensity values. How to compute the mean of my intensity values of an image? I give you an image, and I want to have the mean intensity value. I iterate over all pixels, I sum up the intensity values, and then I divide by the number of pixels. So we'll end up with something like this. So these are just loops over the rows and columns. And so I add up all the intensity values and divide by the number of pixels that I have, which is n. So this is the mean. And again, this is a computation time which is linear in the number of pixels. So I need to visit every pixel once. I need to sum up that value. And so I need to do n operations, or constant number times n operations in order to do this computation. What happens if I know the histogram before? Let's say I have the histogram and want to compute the mean. How can I do that? Yeah.
Ich kann alle xi und alle y's des Histogramms miteinander multiplizieren durch n-Teil, dann habe ich auch.
Exactly. So you just need to iterate over all the bins of the histogram and multiply the value of that histogram, at least of the normalized histogram, times the grayscale value. What's the complexity of this operation? Sorry? Yeah, it's a constant time operation because I don't need to iterate over, I don't need to revisit the individual pixels. It only depends on the number of gray values that I have, which is typically a constant. So what changes, I just need to sum over all possible gray values, intensity values, and multiply the intensity value with the probability that this occurs, which is a value I directly obtained from the histogram. That's great. So this is something which I can do faster than operating on the image. So if I have the histogram, I can do this value more efficient. What about the variance? Actually, it's more or less take the definition of the variance, put it in. I can again work on the individual image, so I sum over all pixels, take the gray values, see how much it deviates from the mean, square it, sum it up, and we are there. Again, if I do that based on the image, it's a linear time algorithm because I need to visit every pixel. And again, if I have the histogram given, I can do exactly the same trick as I did before. I just compute for every gray value deviation from the mean squared times the probability that this occurs, which I have from the histogram, and then I end up with a constant time algorithm again. So mean and variance I can compute in constant time given I have the histogram, and if I don't have the histogram, it's a linear time operation. Okay, so what about the median, or the median? It's again similar as the mean, an estimate about the brightness. The only thing is that it's kind of robust against outliers with a few extreme values in my histogram. So if I, for example, take the median of 0.5, that means also the median of a value G. So if the median of my image G, of the intensity values of my image G, tells me that 50% of, or approximately 50%, because we have a quantization error here, is larger and smaller than this value. Okay, so I can use my plots again. So if I compute the median, that's actually this value over here. And this is exactly this value where the cumulative histogram shows the value of n². So in order to compute that, I just need to go through my either through my histogram and sum up all values until I reach n², or I walk through the cumulative histogram and stop as soon as I obtain a value of 0.5. So now we know how to compute what a histogram is of an image and how this histogram actually tells me something about the image. So far we only did kind of an analysis. We have an image, we compute the histogram, and the histogram tells me something about the image. In the remaining part of the lecture today, I would like to look into what happens if we want to do transformations, if we want to change the image or do an operation which we, for example, compute based on histogram, do an operation which then changes the image, maybe increase the contrast, increase the brightness, and operations like this. So typically there are different types of operators, and we're looking to basically three operators. The first one are so-called global operators, the local operators, and the point operators. The global operators, they work on the overall image. So they consider the overall image, compute a transformation, and then transform the image into a new image. So every pixel, so if this is kind of my input and my output, and this value over here may influence this value down here. So whatever sits here in the corner may have an influence on the center pixel in the output image. So there's an influence. Every pixel may influence any other pixel between input and output. In the local operators, I typically, for doing this transformation, only take a local neighborhood of an image. So in order to transform a point, it only depends on its neighborhood. Typically, this value over here typically doesn't depend on any value down here. Of course, if we increase this size, at some point in time, you end up in global operator. And the point operator is something we look into more specific today, where you say there's just one single pixel which influences the one, which is the one with the same pixel indices. So I do the mapping from an intensity value to a new intensity value only based on this pixel, not based on any other pixel. It's kind of the key distinction between them. Yeah, that's just basically what I've told you here. So how does it work? So let's say from now on B is always my output image and A is my input image. So I have an input image and I want to transform that through a function f so to obtain the output image B. And we're looking here so far in point operators. So every operation in here is done based on an individual pixel. So only the pixel ij in the input image influences the pixel ij in the output image. So this is one pixel in the output image, ij. Well, this is our input, the input image, and this p is a parameter that describes this is needed to compute the operator. So if it's, for example, a linear function, that's the slope and the offset that we have. So this is example. The most basic transformations are linear transformations. And in this case, this function f has this form, k plus m times a. So my parameters are k and m. And then if I want to transform the pixel ij, I execute exactly this term over here and get my function value b out here. Okay. How does this transformation changes the mean and the variance of the histogram? So if I compute the histogram of A and transform it through that image, how does it change the histogram of B? Does histogram stay the same or is it changed? So let's take a simple example. I have my input image, and let's say m equals 1 and k equals 1. That means I transform the image, and every intensity value, I add 1 to it. That's what happens. M is 1 and k is 1. The only thing I do is I increase every intensity value by 1. How does it change the mean? How does this change the mean? It hopefully increases the mean by 1. Okay, and so what we do is we have the k is added to the mean, and of course the scaling factor also scales the mean. So if I multiply all input values by 2, the mean is twice as big in the output image. And with standard error propagation, I can do exactly the same for the variance. So for the standard deviation here. So the standard deviation is the absolute value of m times the original standard deviation. This results from the variance is m squared. The new variance is m squared times the old variance. Just depending if m is positive or negative. Therefore, I need to take that into account. Therefore, we have the absolute value over here. So for this linear transformation, the mean of my output image B can be computed directly from the mean of the image A, and the same holds for the standard deviation here. So what happens if I take this transformation and I have a value of k, let's say I keep m equals 1 and I make k larger than 1. M is 1 and k is larger than 1. Which impact does this have on my image? So my function f of a is k plus a. What does this operation do for k larger than 0? How does this change the visual appearance of the image? If I increase the intensity values by every intensity value is increased by a constant value, how does it change the image? Exactly. The image gets brighter. Perfect. What happens if k is smaller than 0? Makes it darker. Okay. So now let's say we keep k equals 0, and we take a value of which we change the value of m from 1 to a value that is larger than 1. So if it's larger than 1, the variance gets the standard deviation, thus also the variance gets larger. What does it mean if the variance gets larger? I told you that before. This leads to increased contrast of the image. And if we have a value between 0 and 1 for m, it decreases the contrast. What happens if I set m to minus 1? Sorry? Nothing. It doesn't change the standard deviation, but it changes the mean. Right? That could happen if I don't set k appropriately. I would end up outside the. But let's say I choose k in a smart way, so that I still get intensity values between 0 and 255. Exactly. I get the inverted image negative. That's exactly what is been summarized over here in words. So you can look that up. And these are images how they look like. So this is my original image. So there's kind of no change to the image. If I do a transformation like this one, where m takes a value of approximately 0.5 over here. So it decreases the contrast. Just kind of, this part of the histogram is simply compressed to this area over here. So I get this bright image with reduced contrast. If I do the same, but don't add that constant factor, so keep k equals 0, I do the compression in this area, so I get a dark, low contrast image. Or something in between. And this is exactly the example that we have with m equals -1 and k equals the maximum value. Then you have here the negative. Okay, so these are all linear transformations. So the key question is, does the linear function that so if f, I said f is a linear function, that's clear, but does this really lead to a linear transformation of the intensity values? Intuitively, you would say yes, because I changed the intensity values. But we need to take care in here that the intensity values have to be values between 0 and 255. And therefore, we can introduce an error. So this is kind of my mapping from A to B. And I have my linear function over here. If I do this mapping, let's say I take the input value of A equals 0, that would be mapped to a negative intensity value in the image. And that's something which my image typically can represent. So what happens in reality, that every values which are smaller than 0 and all values that are larger than 0 are simply clamped. So I actually end up with this red curve over here. So I need to take care that the linear function f really leads to a linear transformation of the intensity values. This may not be the case due to this saturation value. This especially holds as m is larger than 1. If m is smaller than 1, I typically end up with values over here, then this is not critical. But still, it can lead to the fact that two intensity values are actually mapped to exactly the same value. Of course, I still need to do a rounding operation. Okay, this is kind of clear? That a linear function, f, does not necessarily lead to a linear transformation of the intensity values, just because my intensity values are bounded between 0 and 255. Okay, so these were the linear functions, or linear transformations. Let's look to the nonlinear transformations. So there's a very simple example, which is thresholding. So that means I just get two values, b0 and b1. This can be 0 and 255 or 0 and 1. And whenever in the input image the gray value is smaller or larger than a value t, I get one value and the other value in the other case. So in the end, if I do this thresholding operation, I have only two possible values in my output image, b0 and b1. So if I choose this as 0 and 255, it will be black or white. For what could such an operation be useful? Why may this be a useful operation? So one relevant operation is to create a mask, for example, to separate foreground from background. Let's say I have my near-infrared image that I've shown at the beginning of the course today of the vegetation. And I say, okay, everything which has a really high reflectance value, so really high intensity value in my near-infrared image, is likely to be vegetation. So I can make this value t pretty large. So b0 means there's no vegetation, b1 means vegetation. It would be a very simple way for separating foreground and background, if I'm, for example, interested in vegetation and want to separate that from anything else. So, well, in the end, this function this function f looks like this, so it's not a linear function anymore. It's here, everything is 0. It's a step function, so it's not a linear function anymore. So every value in this area will be mapped to 255. Everything in this area will map to 0. And of course, I can do exactly the other way. Can do it also exactly the other way around. And there's a special case if the output values are just 0 and 1, there's something what we call a binary image. Of course, it's just binary values. So in order to encode that in memory, I typically just need a single bit per pixel. I can store it in a very compressed way. And we will actually look into binary images next week. So a full lecture about binary images and typical operations on binary images is something we are going to look into next week. As I said, what are applications for this, for these operations over here? As I said, foreground-background separation. And this, however, requires that the two things are the case. First one is I can determine my parameter t, and the foreground and the background can actually be well separated. So if I have a small example, say I have a histogram, and this is one part, this is the background, and I have here the foreground, and I know about these distributions. That's very easy. I can just select, okay, my T sits somewhere over here, and I'm done. Foreground, background separation. Okay. I can also do that if I, for example, know the ratio between foreground and background pixels, and they don't overlap each other. I can also find this value T by just starting here, increasing the value until I reach the ratio, the known ratio, and then I have them separated. In practice, however, this is not very often the case. But in practice, it may look like 1 and 2, foreground, background. Oh, let's say. If I have a case like this, I cannot perfectly separate foreground and background. I may select the value t somewhere over here to make the smallest possible error, but in this case, I cannot perfectly separate foreground and background anymore, at least with such a simple technique. Okay, let's say we have this case, or such a case. But we still can make the assumption that we have a bimodal distribution over the occurring intensity values. So, I mean, foreground, let's say, is darker than background, for example, or brighter than background. And one way to actually find the separator here is, okay, let's go to the probability distribution and approximate both the foreground and the background, distribution of intensity values for foreground and for background by the Gaussian distribution each. So what I can do is, I can say I assume I have a sum of Gaussians, in this case 2 Gaussian distributions. So the probability of foreground and background intensity values. And then I have simply a bimodal distribution over here. And then I have the weighing factor, which the weight for the first and the second Gaussian, the mean and variance of the first and second Gaussians I have here as well, and I may estimate them from my histogram. So this is a result how this could look like. So let's say this is a distribution, and this was the distribution for the background, for example, and this is the example for the foreground, and this is the resulting equation that looks like this. What I then actually need to do is I actually need to come up with a classifier, and the classifier tells me, given an input pixel, is this foreground or background? And this is my simple thresholding function over here. So that would be a simple classifier, which either says it either belongs to the Gaussian with mean and variance 1 or with mean and variance 2. And the question is, where should that threshold be? To make the smallest possible mistake. Where would you separate foreground and background? Would be that this one a good idea? Not really. Something over here? Maybe something in here? That's a pretty good point over there. Where, so the error that you do is the probability mass which sits in this tail and in this tail is the probability of making a mistake under these distributions, if these distributions are correct. So, and estimating this allows us to come up with this thresholding value to perform this operation. But there should be a warning, and this warning is this never really works in practice, or it only works in very, very well-engineered situations. So this is a small example. This is a picture of some vegetation, some concrete, and this is such a simple thresholding operation trying to identify vegetation. So vegetation is my foreground, everything else is background. You can see that it roughly works. So the grass in here fits here, and it's done so that the piles and the concrete here are not classified as vegetation. But we can also say already here that there are a lot of mistakes. The images are classified as vegetation, and even here are areas in the green where it's not classified as vegetation. It gives a very, very rough separation of foreground and background. And typically those simple thresholding algorithms are never sufficient to do any, let's say, difficult task. Either the problem is very well engineered, I can perfectly control the object that I have in there, I can perfectly control the lighting, then this thresholding may work. But in a lot of relevant application, working with different kind of input images, that actually doesn't work that well. Okay, this thresholding, as described here, is this actually a global operator or a local operator or a point operator? So far we only talked about point operators. What about this thresholding operation? Why is it a global operator? Yeah, but okay, so this is a point, then I may have not explained it very well. Also, the point operator transforms the full image. The only thing is that the value of the output image only depends on the corresponding value of the input image. So if I take this thresholding into account, so for one pixel in A, I check if it's larger or bigger and set the corresponding pixel in B, the pixel with the same indices, I and J, to that value. I do that for pixel 1, pixel 2, pixel 3, and so on and so forth. And if there's a dependency between this A and the corresponding, so the pixel, the input pixel and the output pixel, if there's only a dependency between the input and the output pixel, that's a point operator. If all pixels influence a single pixel, then it's a global operator. So again, I rephrase my question. Is such a thresholding operation that I do here a global or a local operator or a point operator? Yeah, perfect. So it looks like a point operator, but in practice it's a global operator. The global operator is determining the value for t, the threshold value. Once I have the threshold value, it's a point operator because I can make it on a pixel by pixel basis. Okay, that's exactly. So I move from here. Actually, it's a global one to compute t. Once I have t, it's a point operator. Another very important step is, so what we did so far, the thresholding, was the thresholding between values of 0 and 1. So we just said 0 or 1. I can also do quantization. Quantization of my intensity values. So a very simple quantization is a quantization between 0 and 255, but I can introduce an arbitrary number of steps in there. And I can say, okay, I want to take my whole intensity space and reduce it to one value, 2 values, 3 values, 4 values, 5 values, 6 values, and so on. So here's an example of the same input image, one with 256 intensity values, the same one with 2, so that's the binary image, just 0 and 1, with 4 values, with 8 values, and so on. That's also something where, where a reduction of the number of intensity values can be used in order to compress an image. So this is a simple form of image compression, because I don't need to store a full byte. I only need whatever, 1 bit, 2-bit, 3-bit, just depends on the number of different intensity values that I want to show in here. Okay, so before I actually continue, that's a pretty good point for finalizing the course for today. So what you should have learned in this last 45 minutes over here is what is an histogram, how to compute an histogram based on an image. You should know how to compute the mean and the variance of such an histogram. It's just about from the image. And you should understand what it means to adjust the variance, adjust the mean of that histogram, that we have simple transformations that change the properties of the image and that can be used, for example, to increase contrast, to increase brightness, and to do simple operations on the image, changing the image into a new image so that it has certain properties. We will continue with those operators and look into different ways for actually obtaining a desired result of the resulting histogram. So I have an input image, I want to transform it so that the histogram of the output image has certain properties. And this can be, for example, used to change the distribution of intensity values to make it a visually appealing image, an image which can be well analyzed, or where certain noise parameters have certain values or are constant over the image. Now that's something we are going to look into next week. We start with that probably for the first 30, maybe 45 minutes, and then we continue with binary images next week. That's it from my side. Thank you very much, and see you next week. Thank you.